This is now part 2 on our discussion of the theory behind lines and planes. We left off accomplishing our first goal. We're now going to see if the parameters we've chosen are actually sufficient enough to tell us about all the points on the line or plane. Okay. I also promised that I would make this idea of a direction more concrete. So I'm going to do that first before I delve in to finishing off goal 2. And I want to start with a little side discussion on this. So imagine I have a 2D grid. This is separate from another one. And I have some ordinary vector. Let's call it V. This is now from like Unit 1 discussion. And we're going to be talking about taking linear combinations of these vectors. That's what this side discussion is about. So one linear combination I can do with one vector that's just scalar multiplication, right? So I could have 2 times this vector. That'd be 2 times this vector. I could have possibly 4 times this vector. That's maybe 3 times this vector. Maybe I could have, let's say, 2.5 times this vector. I could have negative 1/2 times this vector. I could have negative pi of this vector, so that'd be like 3 and a bit. Let's say that's like negative pi of this vector v. And you get the point. So I'm looking at linear combinations of v, which is just scalar multiplication. So this is a really important concept, actually. You talk about it a lot in first year of university in linear algebra, but all of the possible linear combinations of v, every single one. So I'm talking negative pi v, negative 1000 v, plus 1 million v, all of these possible linear combinations. You can imagine them, actually, they define perfectly a line, right? All possible linear combinations, right? So how do we write that mathematically? We can say let C be any constant, so that's any number you so wish, and then just times vector v. And I'm saying let C be any number. C is an element of R. That's all possible linear combinations. Okay, we could do the same for 3 dimensions as well. That still actually defines a line. All possible linear combinations of v is what can define a line. In 2 dimensions, we can even make this concept a bit more, in 3 dimensions, we can make this concept even a bit better. Because in 3 dimensions, if we imagine a small 3-dimensional grid, all possible linear combinations now, so let's say we have a vector v, starting at the origin, and we have some vector u. Now, we can have other linear combinations as well. The linear combinations we choose now, well, we can have maybe 3v plus 2u, so that would be like 1, 2, 3, plus 2u, that'd be adding them tip to tail, like that. You could have negative 1/2 v plus maybe 1u, so it'd be like right here-ish. We could have possibly negative 5v, 1, 2, 3, 4, 5, and then maybe 3u, so that'd be like 1, 2, 3, right? And you can imagine now all possible linear combinations of v and u. We can write similarly as let a be any constant, for V, and B, U. Okay, so that's all possible if we let A and B run through all possible numbers. If you think about it, this is already kind of starting to look like it can define a plane. We can have other combinations such as minus 2U plus V, right? You can imagine all these possible linear combinations are capable of defining a plane. Okay, so the issue is, though, we chose these vectors to be position vectors, so all of these planes intersect at the origin. But this concept, we can easily upgrade this to help us now. Okay, so that's pretty important. We're going to use this concept of linear combinations to help us define lines and planes and complete goal 2. So let's think about this. Let's say I want to define an arbitrary point here on this two-dimensional line. Okay, well, the first goal I have is to actually get on top of the line, right? I need to get on the line. So that I can use the known point for. Okay. That's good. But now what can I do? Well, now I can take a vector that lies along this line. Let's say it's this vector right here. Okay. And now I can use the idea of taking some linear combination to get to that blue point. So in this case, maybe I can take 1, 2, 3, 4, 5, 6, like 6.5, right? So I can take, this is my original vector I defined, let's call this one V. I'm using negative 6.5 V to get to that blue point. So what I'm doing is, I need to actually get on top of the line first. That's a given. But once I get on top of the line, I can use any vector that I want on the line, take linear combinations of it, in this case just scalar multiplication, to get to any other known point on the line. Okay? And we can effectively do that for every point. So if I chose another blue point, maybe let's say this one, this blue point right here, again, I get on top of the line using, so I get on top of the line, again, to this green point, and then to get to this blue point right here, I probably need that original vector, I need 1/2 of that guy. Okay? So the idea is to define, I can effectively do this for all points. So to define a line in 2 dimensions, I can say a line just follows this equation. It's getting onto the line, we call that R0, plus scalar multiplication with some known vector on the line. This is the direction vector. Okay? And that now defines all points of the line. Similarly for 3-dimensional space, nothing is different here. I just need to get on top of the line itself originally. Okay? And now let's say I want to define some vector on the line. We'll use this as our direction. Let's say it's this one right here. And now let's say I want to get to maybe where this bug is at. Well, now I need, this is V. I'm going to need 1, 2, like 2.25. So I'm going to need, 2.25, negative 2.25 of the scaled versions of V to get to that blue point. So it's the same idea, right? to define this line, R, I need to actually get to a known point on the line, R naught, plus C, some scalar multiplication, V. And this now helps me, again, define any point on this three-dimensional line. For the plane, we have a similar idea. So for the plane, again, let's get to a known point on the plane. Okay. Now let's say I wanted to find this blue point right here. Okay. So we can use some direction vectors arbitrarily along the plane. Let's choose these ones. Let's say I choose, let's make them parallel to this plane. So this one, and I'll choose another color, let's say purple, and this one. So let's call this one U, and this one V. Actually, I'm going to make U point this way. It doesn't really matter. And then V will be in this direction. So you can imagine now, from this point, this known point, to get to this blue point, I would need, let's see here, 1, 2, 3, 4, 5, 6. Not the most best vector addition. And then upwards to this blue point. So I need -6 versions of U. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10.5. So to get to that point, I would need -6 versions of U plus 10.5 versions of V. So that would be a linear combination I can use to get to that point, to that blue point. So I can do that for effectively any point on the plane. Any point I so choose. I can use some scaled versions of U and V, add them together, and get to a point. And that now defines all points on the plane. So this equation, R is equal to, we need to get to the known point, let's call that again R naught, plus some scalar multiplication of U, plus some scalar multiplication of V. Okay, that's good. And that completes goal 1 and goal 2. We have now an idea of how to define every single point on a line or plane. And that is all you have to know for actually all of Unit 8. Everything else is just manipulation of these facts. I guess a little tidbit I can give you, you'll see later on. This concept is so important that it gets its own name. We call this the span of V and U. You don't have to know this if you're interested, I guess. It's just all possible linear combinations you can make with V and U. So adding them and taking some scalar multiples. This one, similarly, would be the span of just V. Okay? It's a very special name. And that's it for this video. I hope that helps in your journey to understanding Unit 8. In the next video, I will elaborate on Section 8.1. And we'll see where we can go from there. Have a great day, guys.